Next, let's look at the effects of the nucleophile. So when we're looking at nucleophiles, the real thing that we're looking at is whether we have a strong nucleophile or a weak nucleophile. And so let's start back with our reactions again. So I'll make some kind of a secondary alkyl halide and react it with a strong nucleophile, something like hydroxide, versus a weak nucleophile, water. And in both cases, we're going to get displacement of the chloride by hydroxide, so we get a substitution reaction. But which mechanism is each going to follow? So I think what's important to look at here is to think about what the mechanisms are and what the rate equations look like. So if I have an SN2 mechanism, rate equals K times my alkyl halide times my nucleophile. If I have an SN1 mechanism, remember the rate determining step is the alkyl halide falling apart on its own, so rate equals K times the alkyl halide only. So if I have a strong nucleophile, which of these two mechanisms would be favored? A strong nucleophile is going to show up here in the rate equation, and it's going to make my reaction faster. A strong nucleophile will not help this reaction because it's not involved in the rate equation. So the rate determining step happens without the nucleophile being involved at all. So a strong nucleophile doesn't do any good to help this one. So a strong nucleophile makes SN2 faster. While a weak nucleophile makes an SN2 slower. And since this one makes an SN2 slower, really the only thing that's left to happen would be an SN1. Another way to think about this is that in an SN2 mechanism, whatever my nucleophile is, has to be strong enough to come in and force off the leaving group. But in an SN1 mechanism, the leaving group leaves first. And once it gets here, it's going to be able to react with anything. It doesn't need a good nucleophile because this is very reactive. This one will react with just about anything. So to summarize this, for secondary alkyl halides, because remember for primary alkyl halides they're always going to follow an SN2, and for tertiary alkyl halides they'll always follow SN1. So secondary alkyl halides, if there's a strong nucleophile, then it will follow SN2. If it's a weak nucleophile, they'll follow SN1. And the last piece is the solvent. And the reason that we talk about solvent last is that solvent is really related to the strength of nucleophile. So the question is, if I have a strong nucleophile, so that's what we did in the last section. If we have a strong nucleophile, how does my solvent affect it? So to talk about this, we need to talk about three types of solvents that we can have. We can have nonpolar, we can have polar aprotic, and polar protic. So we'll start with nonpolar solvents. Some examples of nonpolar solvents could be like heptane, our cyclohexane. And these solvents are not going to be good for most of our reactions that we're doing. And they're certainly not good for these nucleophilic substitution reactions. Because we start with polar starting materials. If there is an intermediate, we make polar intermediates. And we also have polar products. So the problem is that most of those things just are not very soluble. In nonpolar solvents. The second kind are polar aprotic solvents. And these are things like acetone, ethyl acetate, tetrahydrofuran, diethyl ether, and these solvents are actually quite good for polar reactions. And they're good for nucleophilic substitution reactions. The third kind are polar protic solvents, and I didn't get into this in the last section, but talking about what protic and aprotic means. So protic means that we have an easily ionizable hydrogen, or proton. And typically that means that we have one that's going to be doing hydrogen bonding. So protic solvents are things with OH or NH. So examples of this could be things like methanol, or ethanol, water, amines, carboxylic acids. Amines and carboxylic acids are more rarely used as solvents in reactions. They might be used more often as reagents. They could be used occasionally as solvents as well. Polar protic solvents are going to slow some of our reactions, and they're going to hinder our strong nucleophiles. Hopefully, you're wondering why. And the reason is that polar protic solvents solvate strong nucleophiles turning them into weak nucleophiles. So they take a strong nucleophile and by solvation it can make it so that it's not a strong nucleophile anymore. So let's take an example. Let's take cyanide. So what happens in solution is that if we have something like, let's take something simple like water, cyanide and water. So the cyanide has a strong negative charge at the carbon, and that's what makes that a strong nucleophile. However, if we have water molecules in here, water is highly polarized with a big delta plus on the protons and delta minus on the oxygen. So what happens is the big delta plus on the hydrogen is attracted to the negative charge on cyanide. And if it's in solution, all around this, there are waters. So effectively what that does is it shields the charge and lessens its ability to react.